I have 5 factories and 5 distribution centers, 5 origins and 5 destinations. These are CIJs, cost of 1 unit of product from an origin to a destination. Here are supplies of each origin. Here are demands of each destination. We need to define these decision variables, XIJs, to find it out how many units of product is delivered from each origin to each destination. This is X41, from origin 4 to destination 1, and then we multiply it by the cost of delivering each unit. I compare summation. This is the total number of units delivered to everywhere from origin 1. And if I copy down, this is the volume of product delivered from factory 1 and origin 1 to all destinations. This should be less than or equal to supply of these origins. And then equal to summation of these values. And this is the total value delivered from all origins to destination 1, and I copy to the right. And it is the total volume of product delivered from all origins to destination 5. I should write a constraint stating that these numbers are less than or equal to these numbers, and these numbers are equal to these numbers. However, because the objective function would be minimization of the total cost, it really doesn't matter if I put equal or greater than or equal. The procedure, the computerized procedure that solved the problem will never exceed these numbers because it will only increase cost, and the objective of the model is to minimize the total cost. Do you think it matters if instead of writing this summation less than or equal to, for example, 15, if I also add minus 15, copy it down, and then state that these values all should be less than or equal to 0. It really doesn't matter. So I can go ahead and do that. Furthermore, I can compare and define over there type 1, 1, 1, 1, 1. Does it matter if I state that? It should be minus 15 multiplied by 1. It doesn't matter, it's still the same thing. So I stated x1, 1 plus x1, 2 plus x1, 3 plus x1, 4 plus x1, 5 less than or equal to 15. Then I brought this 15 to this side, minus 15. And then I said less than or equal to 0. And then instead of 15, I wrote 15 times 1. It really doesn't matter. So I have this summation minus 15 multiplied by 1 is less than or equal to 0. I will later explain why I did this. And here it have equal to some product, these numbers, multiplied by these numbers. So I go ahead, data, solver. minimize this objective function value by changing these decision variables and by having these numbers less than or equal to 0, because I have brought everything to the left hand side less than or equal to right hand side, and right hand side is 0, and these values should be equal or greater than or equal to these values. Okay, solve, and I get the optimal solution. Now suppose this company has decided to reduce the number of plants by 1. Still, that supply summation of everything, and here demand summation of everything equal to supply minus demand. We may be able to close one of these factories. These two we cannot, because then supply would be less than demand and we will not be able to find a feasible solution. So how can we do this? Now I assume these ones as binary variables. I come here and I write y's. These are my binary variables. And here I add them up. Sum of these 5 numbers, which is 5 now. Then I go here, I have already have 15 multiplied by that binary variable, which could be 0 or 1. Go back to solver. So my decision variables are these variables, control, and also these variables. Add summation of these variables should be less than or equal to 4, because now we want to close one of them. Add these decision variables are binary, 0 or 1. Okay? Close. Let me copy and paste the special this here. Solver. Solve. The problem is solved. The first factory is closed. Total cost increases by 165 units, but that is increasing transportation cost. However, we may have saved the operational cost of that company. Now suppose we also have operational costs of each factory. Then the problem will remain the same. The only thing I need to add to the problem, I come here and I multiply these binary variables by their corresponding costs. And then go ahead and add this value to my previous objective function. And my previous objective function was transportation costs. So that is the total transportation costs plus the total operational costs. Solve, and that is our objective function value. Now suppose each plant can operate at two different capacities, low capacity and high capacity. And suppose we have the operational cost of each capacity. Then we come and define additional binary variables. These binary variables are related to low capacity, and these binary variables are related to high capacity. However, the firm will only operate at high or low capacity. Therefore, summation of these two binary variables should be less than or equal to 1. Let's see how do we solve this problem from scratch. Solver. The first thing is to define the objective function value. Sum product. These costs multiplied by the volume of product delivered to each destination. That is transportation costs. And then we have some product of these costs, fixed cost, high, fixed cost, low, multiplied by the corresponding decision variables. And that is my total operational costs. And then my objective function, transportation cost plus operational cost. And I want to minimize it. Solver. Minimize this objective function with respect to x variables and also control y variables. Close. Let me change these y variables to all 0. And then let's come here, equal to summation of these minus y low 1 multiplied by its capacity minus YH1 multiplied by its capacity. So it is x11 plus x12 plus x13 plus x14 plus x15. This should be less than or equal to 15 y low 1 plus 30 y high 1. This is y low 1, this is y high 1. Out of these two binary variables, one of them would be 0 because the plant can only operate either at high capacity or low capacity, and these are the related operational costs. And these are the transportation costs from origin 1 to all destinations, which we have already included both in our objective function. So I have that one. And let's copy this one down. Solver. Add these summations should be less than or equal to 0. And these summations need to be greater than or equal to these numbers. Add these summations one by one should be less than or equal to 1. Add these variables need to be binary. Okay? Okay, the problem is solved. Here we have the optimal transportation plan, and here are the situation which plans, whether they are operating at high or low capacity. Thank you very much for attending this session.